to the organizers for the invitation to this very nice conference and this very beautiful place. So I appreciate both. So thank you. So yeah, I'm talking about quasi-classical limit and renormalization in the Nelson model. And as you can guess from the title, there is some overlap with the talk by Nikolai Leopold on Tuesday. But I will make it precise. Actually, we will see the focus here is slightly different, or rather different. Okay, so this is somehow the last contribution, a very long project with Marco Falconi and Marco Olivier. And I have to admit that the paper is not ready yet, so it will be hopefully in, say, well, a few weeks, I guess. We are just lazy. So no, we're just trying to improve certain basically estimates and stuff like that. So I hope, yeah, in a reasonable amount of time it will be on the archive. Okay, so we'll start with a rather long introduction as usual, and I will save some time thanks to the talk by Nikolai, but in fact I will go through the renormalization, the discussion of the ultraviolet renormalization and the discussion of the quasi-classical limit anyway, just to set the notation, so we'll save just a little bit of time on that. And then I will focus on the main results, which are rather, well, about the interplay between the quasi-classical limit and the ultraviolet renormalization. Mainly, let me anticipate the main result, which is from the dynamical point of view, the fact that somehow the quasi-classical limit and the ultraviolet renormalization commute. That was one of the questions actually raised during the talk by Nikolai. So we are going to see that that's the case at the level of the dynamics. That's actually not the case at the level of the stationary picture, if you like. So that's something which will come out of the analysis. Okay. And then I will finish with some perspectives. So we see. Now that's the slides with the pictures to motivate my work. So I usually start with it. Well, it's just to say that there is somehow an interesting question to ask from the physical point of view. So when you deal with, say, cold atom system and stuff like that in a condensed matter experiment, so they treat the fields which are present all the time in the system to confine the system or to create, say, an optical lattice or something like that, as you see here. Well, this is supposed to be an optical lattice. Hard to say, but it is. And so they treat all those fields as classical fields. So they replace them by potentials, essentially. So say either electric or magnetic potentials. So they don't care about the quantum nature of fields, which is so reasonable in a certain way. But why is it so? So can we show that it is correct to some extent, or to a rigorous extent, you may say? So that's somehow the starting point. Now, let me tell you what is this quasi-classical limit. So what do I mean by this quasi-classical limit? So it's a limit in which, as I said, I want to replace a quantized field with its classical counterpart. And when is it supposed to be correct? When, well, one case in which this is supposed to be true is when the field is very intense. So the state is such that the number of excitations of the field is quite large. Quite large compared to what? Well, quite large compared to the commutation of A and A dagger, so the CCRs, if you like. So if that number of excitation is the average number of excitation is much larger than the commutator, you may think that you can discard one compared to this large number of excitation. Now, you can make it actually rigorous from the mathematical point of view, simply rescaling the variables by introducing a small parameter epsilon, which is 1 over that number. Redefining the say canonical variables up to this pre-factor square root of epsilon, and then so the limit we are interested in this quasi-classical limit amounts of taking the commutator between the new variable A and A dagger proportional to this parameter epsilon. Now you can figure out that when epsilon goes to 0, of course, things become classical in a certain way. This is, in fact, was first, well, okay, it's a very old story, but there is a paper in which this is spelled in details by Ginibra, Nironi, and Velo in 2006. Okay, so this is what I mean by classical limit, and that's just at the level of the field degrees of freedom. So now I want to be more precise about the model, just to tell you what I mean by. So that's the Nelson model. So Nikolai introduced already the Nelson model on Tuesday. So we want to describe non-relativistic quantum particles in interaction with the scalar bosonic field. At the level of quantum state, the space of state is the tensor product of L2 over R3n, that's for the particle. So this capital N for me, and that's going to be the main difference, one of the main differences with the talk of Nicolai, this capital N is going to stay fixed. I'm not going to take N to infinity. The number of particles is given. And the field part is a Fock space, of course, over the one excitation space, which is in this case L2 over R3. Now I'm using this notation, which I hope is useful, I don't know actually. So I'm using colors, so the green color to describe the field degrees of freedom, and the blue color to describe the field degrees of freedom, so to distinguish between that. Okay, let me stress again that in this Fock space we have epsilon-dependent CCRs, so the computator between A and A dagger is epsilon times the scalar product between F and G. So that's the space of states, and so next, what is the Hamiltonian, of course? That's the Nelson Hamiltonian. It's composed of three terms, so we have some particle part, you may say, some field part, and some interaction. So concerning the particle part, you can think of it as being just minus Laplacian plus a potential, perhaps a trapping potential, perhaps just perhaps maybe even zero, doesn't matter at all. We may add some interaction between the particles, but I don't do it in this talk just for simplicity. And we assume that it's semi-bounded and self-adjoint, just to start with. The field, so the second part is the second part of the free Hamiltonian, you may say, is this field part, and that's just the second quantization of a dispersion relation, which is square root of k squared plus m squared. And m can be even zero, so we may treat also the massless case. Actually, I will mention this later, so we can do it for the dynamics, not quite for the stationary problem. There is some parameter here appearing, this new epsilon in front of the field energy. That's going to be an important scaling parameter for the dynamics. I will comment on that later. Just think of it as being either 1 or 1 over epsilon. Okay? In fact, those are the only two relevant scalings. Any other scaling can be recast in this form up to rescaling of the variable. So you think of this being either 1 or 1 over epsilon. So, and according to the limit that you get, either 0 or 1, you may get two different schemes for the dynamics. What is the interaction? It's just the field operator. And as you see, the form factor here is 1 over square root of 2 omega of k, and there is an ultraviolet cutoff. That is a smooth cutoff, so it's just a function which is smooth, chi sigma is smooth, it has compact support, and it is 1 for k smaller than sigma. So sigma is the ultraviolet cutoff in my notation. Now, as Nicolai pointed out, I mean, this is not L2, of course, because unless, I mean, sigma is finite, so if sigma was infinite, you get 1 over square root of omega, which is not L2 because it behaves like 1 over square root of k, which is not integrable, of course. So that's going to be the problem in a way. So for finite sigma, there's no problem at all, of course. So, and everything is well defined. You can prove this Hamiltonian is self-adjoint, but I will come back perhaps to it in the next slide. So, okay, yeah, indeed, here it is. So here you see again, we have a free part of the Hamiltonian and then the field interaction. And you can rewrite, if you like that, if you prefer, with f sigma, which is chi sigma divided by the square root of omega times the Fourier factor. Now, assume that V is positive, again, for simplicity. We can relax all these assumptions, but just for simplicity, and it's L-infinity log, so it's either a trapping or whatever. Then for any fixed epsilon and sigma smaller than infinity, of course, the operator is a self-adjoint. And in fact, this interaction is a small perturbation in the sense of quadratic form of the list of the H free, so it is self-adjoint on H free and is bounded from below with the uniform bound, which is uniform with respect to epsilon, which is going to be important later, but we will come back to it in the next slide. So this was introduced, as you know, by Nelson in 1963, so 60 years ago. So it's the birthday of one of the birthdays, the important birthdays of the Nelson model. And what was pointed out actually in that very original paper by Nelson, also restudied later by, for instance, Grisimer and Wunsch and Lampard and Schmidt and so on, is that you can perform an ultraviolet renormalization. Namely, you can take sigma to infinity, not naively, you have to do it in a proper way, but in the most simpler way you may think of among, let's say, the quantum field theory models. So in such a sense that say, the Nelson model is a playground, if you like, for the ultraviolet renormalization. Indeed, as we are going to see, the renormalization requires only to extract some constant energy, some offset energy, if you like, from the Hamiltonian, and take sigma to infinity, and then you get something meaningful. Of course, the constant that you remove is diverging. So, and it's what is called, it goes under the name of self-energy, and it's a divergent quantity in sigma, and sigma goes to infinity. Okay, let's discuss this renormalization as it goes. Now, for the moment, and for the next couple of slides, epsilon is going to be fixed, so I don't want to care about the semi-classical limit. Epsilon is 1. Think of it as being 1. Then I will come back to the interplay between the two limits. Now, how do you perform the renormalization? The idea is to introduce this dressing transformation, which was actually suggested by Gross before, actually, the paper by Nelson. So you fix some reference sigma naught, which is fixed. This is going to be taken large later, but large compared to, say, 1. I mean, it's fixed from the outset, but sufficiently large to ensure self-adjoindness. I will come back to it. Now, you fix this reference sigma naught, you take sigma larger than sigma naught, and some theta real or real number. Then you can introduce a family of unitary operators, which is in fact a unitary group, if you like. Which gives you the dressing transformation or Gross transformation, if you like. So it's in fact a dynamics, as was pointed out by Nicolai. You may think of it as another dynamics on your system. So the generator is the field operator, but now the function g sigma, which appears there, is not the same as before. Before it used to be f, as you see. So this g sigma is, again, it has more or less the same form. You have the Fourier factor, and then you have some function of k alone. But that function is much better behaving for a k large, as you see, because on top of the 1 over square root of omega, which was already also there in f, now you have 1 over k squared for large k, which gives you 1 over k to the 5 halves, which is now integrable, and that's why you perform this. Well, that's quite important, of course, to give a meaning to this dressing transformation. And look also at the numerator. There is a difference between the two cutoffs, the one at sigma and the other one at sigma naught. So you have no infrared singularities here, because when sigma is smaller than sigma naught, that's identically 0. So that's also important, well, for the massless case, in fact. Okay. Yeah, a key observation of Nelson, of course, is that you may take the limit sigma to infinity to this, well, in this dynamics, in a sense. So you do have a meaningful limit sigma to infinity. You can perform it. Everything is still well defined when sigma is equal to infinity, precisely because of the good decay of this function psi. And therefore you still have a unitary group, the epsilon infinity theta, when you take sigma equal to infinity. So this is going to be quite important, of course, later for the normalization. Okay, very good. Now, what do you do with this dressing transformation? Well, you define a dressed Hamiltonian, and the dressed Hamiltonian is obtained from the original Hamiltonian, h epsilon sigma, so the one with the cutoff sigma, by extracting the self-energy, which is diverging. So here you see the explicit expression of the self-energy. Notice there is the number of particles in front, and there is the parameter epsilon, which is fixed for the moment, but it comes in front of this self-energy. And then you conjugate it with the dressing transformation evaluated at the theta equal to 1, because that's the relevant one to consider. Okay, very good. You define this operator here. You can do it. And what you realize, and that's very key, is that if you take now sigma naught large enough, k epsilon sigma is a small perturbation in the sense of quadratic form of the free Hamiltonian. So the free Hamiltonian, which used to be there before. And this is also uniform in a sense as sigma goes to infinity. So even k epsilon infinity is well defined. It's a proper self-adjoint operator, which is also bounded from below. So that's how the ultraviolet renormalization basically works for epsilon fixed. Because what you do then? Well, you define actually for, again, sigma naught large enough but independent of anything else, sigma and epsilon or whatever. You prove first that k epsilon sigma converges in norm resolvent sense as sigma go to infinity to this k epsilon infinity. And you define your renormalized Hamiltonian as the undressed basically operator for sigma equal to infinity. So you go back with the dressing transformation, but now with the dressing at sigma equal to infinity, of course. Now this is a self-adjoint operator. It is bounded from below just because k epsilon infinity is, and just because you are conjugating it with the unitary operators. But more importantly, if you look at the dynamics generated by the cutoff Hamiltonian, when you subtract the self-energy, and you conjugate in the proper way with the dressing with the cutoff fixed and the dressing at infinity, and you take the limit sigma to infinity, that unitary group converges to the dynamics generated by the renormalized Hamiltonian. And that's basically how the ultraviolet renormalization goes for NASO. Notice that this phase, so I pointed it out already later, before, that this phase diverges. So this quantity here goes to infinity, so there is a diverging phase in a way in the procedure, but you don't see it actually at the level of the dynamics, because if you think of the Heisenberg picture, you have got to conjugate your operator with this kind of operator dagger and the operator itself on one on the left and on the other on the right, and then any constant term will cancel out, of course. So you don't see the divergent phase. It's no problem at the level of the dynamics. Of course, it's not the same at the level of the stationary picture, and then I will come back to it later. Very good. Okay, so now I can tell you what are the main goals of my talk. So, and then I will make more explicit what is this quasi-classical limit I'm focusing on. So the main goal is just to try to understand what is the interplay between limit epsilon to 0 and the limit sigma to infinity. Perhaps, well, do they commute? Can you take the two limits at the same time? And so on and so forth. And this at the level of the dynamics and at the level of the ground state. So you take the infimum of the expectation, or the bottom of the spectrum of the cutoff Hamiltonian, and you ask yourself what happens when epsilon goes to 0 and sigma goes to infinity. In which order, it's also part of the question, if you like. Now, there are several works which are related to what I'm doing, well, say in which the quasi-classical approximation comes out of the setting that you are considering. For instance, Robert mentioned the polaron. The polaron is a case in which you are actually considering a limit of this form. But here I'm more focused actually on the precise questions that are written there. And concerning those questions, actually there are a few works. One is the one presented by Leopold, and I think I made a mistake in quoting it because I think there is Lampard instead of Petrad, right? So I'm sorry. So I think I quoted the wrong paper with the wrong year.
But there's another.
Yes, but that's earlier, right? So okay, anyway, so more or less the same authors, so with one in place of another. Okay, so so key references are the papers by Amari and Nier, where they started this business of semi-classical analysis in infinite dimensions, and a more recent refinement by Marco in 2018. Again, if you consider only the full classical limit, so the one in which you take the classical limit on both the field and the particles, that was done in a paper by Amari and Falcone in 2017. And then there is the recent contribution by Leopold and co-workers, where they do a simultaneous limit in which epsilon is 1 over n, basically, or 1 over n, I guess, right? 1 over square root of n.
No, 1 over n.
1 over n, okay. So they take at the same time the mean field limit for the particles and the classical limit on the field, and they get this renormalized volume theory. And of course there is a list of work we did, and I want to mention also quite recent, actually a pair of works by Breteau, Faupin and Payet, the last year works, where actually they don't investigate the ultraviolet cutoff removal, but still those are important because they investigate the quasi-classical energy. So I will come back later, and they prove existence and uniqueness of the ground state. Those are quite important to me because we have also, so I will mention again those works in the perspectives, and you will understand why. Okay, so from now on, let's now forget about the ultraviolet renormalization and focus on the quasi-classical limit. So I have to tell you what I mean by that in a precise mathematical way. So the particle system will remain quantum. So I'm not touching the h bar, if you like, of the particles. What I'm going to take is a limit as a classical limit only at the level of the field. So the degrees of freedom for the particle, the states will be still L2 over 3n, and the observables are bounded operators on L2 over 3n. And n is fixed again. Now, on the other hand, on the field, I'm taking the limit epsilon to 0, and I expect to get a classical description for the field in the limit. So what do you expect to get? Well, instead of having basically a quantized field, you should find out something which is its classical counterpart. So, for instance, the state, or the pure state, should be points in the phase space. And what is the phase space? Is the one excitation space, so L2 of R3 in our case. What about the observable? The classical observables are functions over the one excitation space, or over the phase space, if you like, the classical phase space, which is still L2 of R3. Well, more in general, what are mixed states for such a classical system? Well, those are measures, probability measures, better to say. Probability measures, well, not exactly over this L2 of R3. Well, it depends. I mean, if you think of states with finite energy, they better have finite energy. In which case, you have to restrict to states which are so that when you multiply by square root of omega, they remain in L2. So it's a slightly, well, in the massive case, it is a subset of this. In the massless case, it is not. The two spaces are not the same. That's going to be a quite important point later, actually. Okay, now, this is just for the field, the second part. This is just for the particle. When you couple the two, what do you get, mathematically? You get an object which is called, which we called actually state-valued measure, or somebody calls it vector measures, or something like that. So it's a measure, you see, which goes from the phase space of the field onto trace class operators for the particles. Of course, I mean, it's just a generalization, if you like. So you take a measure, as in this case, but it should give you a state for the particle. That's why it takes values in trace class operators. And what about the observables? Well, the observables are simply functions from, again, the one particle or the phase space, if you like, and bounded operators for the particles. Okay, is this object well defined? You may wonder. Well, it is. You may define an integration with respect to those kind of measures, which is also, and you also have a very helpful property, which is this Radon-Nikodym decomposition for the measure. Namely, you can associate to any such measure its Radon-Nikodym derivative, which is this gamma m of z. So a scalar measure, if you like, let's call it a scalar measure, which is a measure over L2 omega with values in real numbers, if you like, such that the measure of the full space is the total mass of the original vector measure. But also you have, as I said, a Radon-Nikodym derivative, so a function, which is a trace class operator function, such that when you compute the measure, the vector measure of a given set, or a given measurable set, you integrate over the scalar measure this function. And this provides you with the trace class operator, as it should, of course. Now, this is, everything here is well defined, and you can, well, it's up to you. You may think of a vector of the vector measure itself, or of the pair of the given by the scalar measure and its Radon-Nikodym decomposition. So it's a Radon-Nikodym derivative, if you like. So it's equivalent. So there is a unique somehow correspondence. Well, to some extent, okay. So here is, well, the integration is defined in the usual way. The only thing you have to be careful is the fact that the order matters, is quite important. So if you define the integral in this form with the Radon-Nikodym derivative, you cannot put the measure on the right of the integrating function, right? So it's not a matter of convention. It's really something which gives you the different result. Well, a quite simple example is given by uncorrelated states. For uncorrelated states, the Radon-Nikodym derivative does not depend on the point z, so it's independent of the field degrees of freedom, of course. And in that case, you can take it out, if you like, of the integration, and then this is just an integration, it's a more conventional integration, if you want. Okay, this is a key point in my analysis. So this tells you how one can relate, say, the quantized field with, or rather, see, the microscopic model, so the model with epsilon different from 0, to its quasi-classical counterpart. So there is a topology in which you can associate, basically, to quantum state their quasi-classical counterpart. And the topology is given by this definition here. So I'll go through it, and if you have, well, if there's something which is not clear, just ask questions. So Now you start with a family of states, say density matrices if you like, trace class operator with trace equal to 1, on the full Hilbert space, so the tensor product. Now you define for such a family the associated set of quasi-classical Wigner measures as the limit points, in a sense, when epsilon goes to 0 of that set. I'm sorry, there is a misprint here, there should be gamma of epsilon. What is this set of limit points? It's the set of vector measures such that there is a convergence along a subsequence. Of course, you have to extract a subsequence because in general you have no convergence actually on any sequence you take. But in what sense there is convergence? The sense is explained here. Well, it's a bit, okay, later I will translate this in the scalar case, so when there is no coupling with the particle subsystem. That should be a bit clearer, I guess, but let me give the definition anyway. So you evaluate the expectation over your sequence of the Weil operator on a given point eta, which, well, forget about this, which belongs to the one particle, to the phase space, to L2 over 3, if you like. Here, so you're requiring a little bit more, but it's not important. And then you tensorize with the compact operator for the particles. You take the limit n to infinity, and you ask that this quantity converges pointwise in eta to the Fourier transform of the measure. This is the Fourier transform of the measure. Okay, what would you call the Fourier transform of the measure? Evaluated again against the same compact operator. And this must be true for any compact operator. Okay, this is the topology we are defining. So a simple way to say is that this topology gives you the convergence of the Fourier transforms of the state to the Fourier transform of the measure, except that of course the state is a quantum state. It has it's Fourier transform. I mean, it's not a Fourier transform of a measure, but well, it's what you may call the non-commutative Fourier transform. This is so the expectation with respect against the Weil operator is what you would call a non-commutative Fourier transform. And when epsilon goes to 0, you do have convergence. Yes.
So is it something like the Wigner transform on the level of the field?
Well, here you are in infinite dimension. If you consider the finite dimensional version of it, well, there is of course a relation. Yes. Well, that depends on the choice of the variables that you take, either x or mp or x plus IP and x minus IP, which is z and z bar here. So it depends, but it depends on the way you want to write the symbol, if you like. But yes, it is related in some sense. Okay, so let me give you the simplified version. So that's for the scalar case. When you have no correlation between the particles and the field, then you just look at the field and you ask then when there is convergence when the density matrix for the field converges to a given measure. Now it's a scalar measure, so the random derivative is just constant. And you see, this is the topology. So you take the expectation with respect against the Weil of the density matrix, and you require that for any given eta, you have convergence to the Fourier transform of the scalar measure. This gives you exactly a topology, which makes sense, which is a sort of weak star topology, of course, in the proper set. Just to give you an example, so you may ask yourself, what do I get in the limit? A very simple case is the case in which you have a coherent state for the field, so still uncorrelated. If you take a coherent state for the field of this form, well, properly rescaled because we have epsilon in the picture, so the Weil operator acting on the vacuum, properly rescaled. The classical measure associated to it is the Dirac mass centered at L0. Okay? As you know, the coherent states are the most classical ones, and this is why actually their counterpart are pure states. Yes.
Did you say that the classical field converged in an L2 or L1? Something L2 or L1?
Well, okay. Well, in terms of operator, you mean because that depends. Classical field is an operator, so it's not a state. In what sense do you want to?
I just had understood that the classical field.
The expectation, you mean?
Yeah, maybe I'm not understanding then what it is, but I was still seeing the delta as something that's not an L2, so it was kind of scary.
Okay, yes, no, but here we are, well, this is just a very weak topology, and this, you should think of this as a measure living on the Hilbert space. So As a measure, it makes sense. It just singles out a single point, and if you want to integrate a function of z against this measure, just gives you the value of the function in the point.
Okay, perfect. Yeah, thank you.
Okay, so I think now I can finally state the first result. So that's the theorem, which takes one slide, as you see, but I will go through it rather slowly. So the first quantity I have to define is this nu, which is the limit of epsilon against nu epsilon, and this is either 1 or 0. So there are two options actually, no more than that. I take an initial datum, so which is a density matrix for the full system, so which is a trace class operator with norm equal to 1, and I require that it has a finite energy uniformly in epsilon. That's key. Well, actually, this may be relaxed, but I will come back to it later. Then the first thing you can prove that the limit points, the set of limit points is non-zero. So there are quasi-classical measures associated to this sequence, if you like. And for any such limit point, so for any vector measure which is in the limit point, then you have a commutative diagram in which you start from the full quantum state for your system. So, well, actually the subsequence, actually, gamma epsilon n. And then you can do two things. Either evolve with the renormalized Nelson Hamiltonian, and you get time t, so that's the usual dynamics. And then you can take the classical limit, and you can do it either at the initial time, and then you get the measure. If you like, you can think of this m as it's a Radon-Nikodym decomposition, so the Radon-Nikodym derivative and the measure, and I think I revert the order was reversed before, so I'm sorry for that. But anyway, I mean, this is the Radon-Nikodym derivative, and that's the measure. And you can also think of the evolution of it. So the time evolution of it to match with the time evolution at the microscopic level is given by something, well, not too weird, but not too simple. So you have to evolve. First of all, the Radon-Nikodym derivative with a unitary operator, which is a two-parameter unitary group in general. I will come back to it in a second. And then you have to push forward the measure. So the push forward of the measure is done through a factor which is quite simple. It's a multiplication operator. It's e to the minus it nu times omega. So in particular, if nu is 0, you don't do anything. So you don't push forward. The measure stays constant. If on the opposite, nu is equal to 1, you have a push forward which is non-trivial on the measure. Now, what about this? So it's a two-parameter unitary group. Again, if nu is equal to 1, and the generator of this group is an Hamiltonian self-adjoint operator, which depends on the Z, which is, I recall you, the classical state of the field. So it's given by the unperturbed part for the particles, and then the counterpart, or the classical counterpart of the field operator. This is just a function. It's an operator which is a multiplication operator, but it depends on the field degrees of freedom through this function Z. So, this is a fancy way to write it, but in the next slides I will write it in a slightly different way. Anyway, it's a bounded potential in this setting here, and then you see this might be time dependent if nu is equal to 1. If nu is equal to 0, there's nothing, no time dependence, and this is a one-parameter unitary group actually in that case, and it generates this evolution of the Radon-Nikodym derivative. So. Now I'll make infinitely many comments about these slides, but yeah, okay, so the first important comment is that this suggests, or this tells you in a way, that renormalization and quasi-classical limit commute. So they are transparent one another in a sense. So you can either take the normalization at some point, and then after the quasi-classical limit, or the other way around, and you get the same result. So at least at the level of the dynamics, I mean. So as I said, I wanted to make several remarks, but if you have questions, perhaps about the statement, if there is something you find obscure, otherwise I'll make the comments. Yes?
What's the corresponding dynamics?
What is this? What does this, you mean?
Yeah.
Okay. Yeah, that's not totally obvious. Okay, put it like that. In one case, it's easy to figure out. So, and the one case in which is easy to figure out is precisely the one of coherent states. So for coherent states, this is a delta measure. So the state of the field will remain equal to the initial state up to, in case, to some, well, free evolution or no evolution at all, because if nu is equal to 1, you have free evolution of the field. If nu is equal to 0, you have no evolution at all. And the particle is evolved with an Hamilton, with an operator actually which depends on the initial state of the field or the evolved state of the field. That depends whether there is evolution or not at the level of the field. So in that case, you can immediately figure out what it is. In general, it's just what it is. I mean, it just tells you that, that the combined state of your system is something rather complicated, which, in fact, this evolution is not even Markovian. It has a memory, actually. And it is a memory in the sense that it's, in general, say, for nu equal to 1, you have no group property. So if you take the evolution from time s to time t, from time t to time, say, z, whatever, then that's not the same as taking the evolution from s to z. Okay? So the group property is not satisfied by this kind of evolution. In general, I mean, in general. For the case of coherent state, it is. Because for coherent state, well, I will come back later, perhaps, to it. For coherent state, everything is quite special. Okay, perhaps I'll come to the comments. Okay, here you see that's the comment about the. Oh, sorry, that's the comment about the coupling. So the fact that the dynamics of the field is well, that in a sense doesn't feel actually the particles. Because it is either frozen for nu equal to 0 or free for nu equal to 1. That's quite different from Nicolai's setting. And the reason it is like that is because we are not coupling actually the limit, the mean field limit with the quasi-classical limit. We have just one quasi-classical limit at the level of the field. So we don't see any back reaction. That's it is what it is. So this is a second comment I've already made, namely, the dynamics for the dynamics for the full system in this quasi-classical limit is something quite well, not that common, I would say. The reason, well, you may think of it. So think of you may trace out the degrees of freedom for the field if you like. That's something you can do, and you will figure out that for the density matrix for the particle, we have the dynamics which is as this form. And this is much more familiar. That's a typical unitary evolution that you get for time-dependent Schrödinger operators. But the most important problem here is that everything depends on z, on the field state. So you have to integrate afterwards over z. That's why you lose all the properties of the group. Okay? So the integration of over z is taken afterwards. That's why you get something weird for this kind of evolution. Unless it's a Dirac mass. If it is a Dirac mass, you have no problem, and the integration is just evaluation. Okay. Well, okay. This is probably over. You have already guessed that. So the counterpart of the field operator, the classical counterpart of the field operator, is precisely the potential appearing in the generator of that UTS, in that group UTS. And that's something you can realize immediately. That's the classical symbol associated to this expression here. I made a mistake here. That should be infinity, not sigma. So after the ultraviolet renormalization, that's what you get. And that's the last comment. I've already made it. So we see no interplay, no basically surprising interplay between renormalization and the classical limit. So in particular, you might take even you can even remove the cutoff as a function of epsilon and take epsilon to 0, and you expect to see nothing new actually. So you expect to see the same exact result. Okay, so what about the stationary problem? Now, for the stationary problem, the things are slightly different. Now, okay, one thing I wanted to point out a couple of things more, perhaps. Well, okay, at least one. The result for the dynamics holds even for the massless case. So this is under the assumptions I made at the beginning, that is for m even equal to 0, we can prove this. And as I said, we can perhaps even improve a little bit this class of initial states. This is a very restrictive assumption. We may probably get something like C nu epsilon here, but okay, this is what we are actually checking now before completing the paper. So this is for a massless case. Concerning the stationary case, I have to restrict actually to the massive one, so I have to take the mass positive. The reason is a technical point, which, well, a technical step in the proof, which is a key step of the proof, and we cannot, at the moment, we don't know how to solve it. And I'm also fixing that nu epsilon equal to 1, of course, because we want to put all the energies on the same ground, right? So we want to have a contribution of the same order from the particles and from the field. So. Okay, so what is the energy we expect to get in the limit in this case? Well, that's what Robert called the Pecard functional. One way of calling it is the Pecard functional, but okay, rather the Pecard functional is the one you get when you minimize this with respect to the field state. So you just take the expectation of the quasi-classical operator Hz we have seen before over a state for the particles, and you add the field energy, so the L2 norm of square root of omega times z. Now, as I said, the Pecard function is what you get out of this when you minimize with respect to z. You can do it for any model of quantum field theory, so in the case of the polaron, you precisely get what is called the dependent. The ground state energy is what you get by taking the infimum of this expression with respect both the particles and the field. So you take a joint minimization problem. Okay. Very good. So that's the energy we expect to get in the limit. Are we able to show that you will get it? Yes, that's the theorem. And this says exactly that the bottom of the spectrum of the normalized Nelson Hamiltonian, keep in mind that the normalization has already been performed. So the limit epsilon to 0 of it is precisely this quasi-classical energy, which makes sense even without cutoff. You don't care about the cutoff because at the quasi-classical level everything is okay, even if you remove the cutoff. Now, in addition, if and only if actually H naught, so the free particle part, which is minus Laplacian plus V, as compact resolvent, so if the potential is trapping, and the reason why we need this assumption, perhaps I will tell you later. Under this assumption, and if you take a sequence of approximate minimizers, so basically a sequence of states which have an energy close to the ground state, up to a smaller order term, higher order term, then for such a sequence of state, we can prove that the limit points, the set of limit points, is non-empty, and what you get in that set is given by measures concentrated on the set of minimizers of the quasi-classical energy. And in particular, in fact, well, it's of course implicit here, we prove that we do have a minimizer for the quasi-classical energy. So the proof that there exists a minimizer is of course needed in order to make sense of this sentence. Otherwise, it makes no sense. Very good. Okay, so I'll skip for the moment the comment about the compact resolvent. Perhaps I'll come to it later. But this is the counterpart, as you see, in a sense, for the stationary problem, except that we have the restriction to massless, to the massiveness of water. Okay. One way to see that this assumption about the compact resolvent helps is the fact that when you assume it, and when the field is massive, you know that the Nelson model has a Fock ground state, which helps a lot, of course. So, but that's not the reason actually we have to assume that it has compact resolvent. So it's a more subtle reason which has to do with the quasi-classical limit. Okay, yeah, or rather, okay, in the proof of this result, we use this information, we use the fact that the field is massive to exploit a certain bound, which I will perhaps comment later, which comes out of a sort of pull-through formula, and that's not available in the massless case. So, and for that we need actually the existence of the Fock ground state for the Nelson model. So it's a bit involved, but this is why we have to restrict the massive case. But the compact resolvent assumption has also another source, another reason which I don't want to comment for the moment. And it's also known that for m equal to 0, the ground state may be no Fock, and in which case we do expect to be able to do something, but we still have to investigate the question actually. Well, for those of you who cares about it, it's, this result may be reformulated also in terms of gamma convergence. We believe, we still have to fill all the details, but I think that's a bit interesting because it gives you also some sort of stability of the minimizer with respect to perturbations. Now, concerning, okay, so that result tells you what you would expect, but then you ask yourself, can I perform first the quasi-classical limit and after the normalization on the other way around, or can I perform both at the same time? Well, that's somewhat more subtle in the stationary picture, because if you assume that your cutoff parameter sigma depends on epsilon, and it goes to plus infinity as epsilon goes to 0, now you take the ground state energy and you ask yourself, do I get the quasi-classical energy in the limit? Well, that depends on the speed, of course, of the cutoff removal. And that's perhaps quite simple to figure out. Why? Because the self-energy is logarithmic divergent in sigma. So this quantity here diverges logarithmically. You figure it out immediately because that goes like 1 over k squared, 1 over k cubed, and then when you integrate, you get the logarithmic divergence. And then you see, we have a threshold. So if sigma epsilon goes to 0 too fast, faster than e to the 1 over epsilon, then you have no connection between the two variational problems. If it goes at the same speed, so at this threshold speed, we get a correction which is finite, and below the threshold we get the quasi-classical energy. But that's somehow obviously it's an obvious consequence of what we said before. But you see, this tells you that the two limits do not commute in the very proper way, in the sense that you cannot perform the normalization too fast. Somehow. Yes.
So the reason that you can kind of then you can make it kind of epsilon dependent is because of your scaling the self energy scales like epsilon.
The self, yeah, okay. Wait, the self energy, well, the E epsilon sigma is this, but it gets multiplied by epsilon.
Epsilon and
yes.
ln
yes.
logarithms
yes.
of the cutoff parameter.
Exactly. So you have a quantity which goes like a capital N number of particles, epsilon, logarithm of sigma. And that's why you have this threshold. That's exactly how it goes. Okay, so I think I made all the comments in this slide. So what time do I get? So it's no time. I do have 5 minutes. Very good. So now, well, okay. I'll first tell you something about the perspectives, and perhaps I'll show you something about the proof if you want or not. Okay, we'll see. Now, we are doing something more simpler, I would say, but still, with some interesting outcome. So the idea is to, instead of doing the full analysis, to restrict to product states. For product state, you can do everything, in fact, because when you have product states, you have uncorrelated states. Everything is much simpler, you can guess. And for the Nelson model, there's not so much to prove. You get the result for free in a way, so convergence. You restrict to product state. But this is not so trivial for the Pauli-Fierz model. So the removal of the ultraviolet cutoff at the level of product states for Pauli-Fierz is not that trivial, and that's what we were actually investigating. And this is interesting because one can extract a speed of cutoff removal at which you can perform a sort of renormalization over product states for Pauli-Fierz. And well, that somehow also may give some information about the self-energy in the Pauli-Fierz, of course, which cannot be ultraviolet nor normalized as the Nelson model. And there are two questions I've already mentioned. One about the massless case, so the completion of the result, say, for the ground state energy in the massless case. And well, again, what happens to the Pauli-Fierz is actually what we aim at understanding in a sense for the future. So, okay, let's keep the attention and let's keep the thank you for the attention. I'll go to just a quick sketch of it. No, it's just a couple of slides. I don't want to thank you all. Alright, so you have to go for that. Okay. No, well, just to give you a very, very quick idea of the proof. The proof goes like that. So you start from an initial state, say a pure state, just to simplify things, and you act with dressing, the epsilon infinity. And then you get a new one, fine. That's a unitary transformation, so it does nothing basically. And then the evolution for such a state is driven by this K epsilon infinity, which is the dressed Hamiltonian. So in a sense, in order to complete the proof, you have to address this dressed evolution. Okay. To look at this expression here, basically, and prove everything for this expression here. Now, okay, then separately you may address the limit epsilon to 0 of the dressed transform, and if you put everything together, you get the result. That's basically how it goes, the proof. So you can separate basically the problem into two different problems. The first one for the dress dynamics and another one for the dressing. So by doing that, because the dressing is a dynamics, as Nikolai pointed out. Actually. Now, what are the problems in this approach? The first one is that the generator, this K epsilon infinity, this generator of the dressed or this dressed Hamiltonian, is quadratic in the creation annihilation operator. That's not too bad. We started from the Nelson Hamiltonian, which was linear. That's quadratic, but that's not a big deal. It is a little problem. But more importantly, there are terms which combines the gradient and the creation of an annihilation operator. So an unbounded operator for the particles times some creation annihilation operator. So let me go back. So yeah, sorry. So here is what is okay. Don't look at the slide. Just look at the fact that when you compute the dressed Hamiltonian, there is some unimportant part, but the key point is that inside this interaction here, you have terms where you have the gradient for the particle coupled to the creation operator, and there is also some k inside actually the creation annihilation operator. So. And those terms are the most annoying ones because they are unbounded for the particles and unbounded of course for the field because of the presence of the creation operators. Last but not least, another big problem is the fact that you want to start from an initial state as good as you want, but you need to propagate the regularity at later times. And the propagation of regularity is a big problem in this business. So, okay, well, here is how the proof goes basically. So the fact that you have those unknown terms, in fact, is something we treated already for the Pauli fields model, because in Pauli fields you do have quadratic terms, you do have terms involving the gradient and the creation and annihilation operator. So we had the technique to handle actually those terms. What is the technique? Well, it's the quasi-classical analysis I described before. Basically, everything relies on the semi-classical analysis rather than infinite dimension, which was developed by Amari and Nier. So you need some control a priori on your state, and then once you know that, you know that the expectations of a certain observables, well, symbols of a certain kind converge, or sorry, quantization of symbols of a certain kind converge to their classical counterpart. Now, the key problem we figure, or the most important problem actually we found is the fact that we had to exactly choose the proper initial regularity and propagate. And the initial regularity, at least, well, in the first step of the proof, has to be something like you need a control, a uniform control on the expectation of the, say, the number operator, or the second quantization of omega, so the energy of the field, to a power strictly larger than 1. You need it to control the singular terms basically appearing in the dressed Hamiltonian. And okay, so that's the most important technical ingredient of our result is this pull-through formula, which we used actually to do that control, and which allows you to bound the norm of the action of this d gamma of omega to a certain power alpha. Or sorry, this shouldn't be omega to the alpha; should be just this f. I'm sorry. So the gamma of this f in terms of the norm of the Hamiltonian. So this gives you the control on this quantity to the power 2, so the expectation, and then with that you can propagate the bound, because of course the bound for this quantity will propagate over time, because it commutes of course with evolution. Now the function that we put inside the gamma here is this function f, which behaves like omega for small k, the infrared, and behaves like k to the alpha for large k in the ultraviolet region. So, and that choice allows to perform all the limits and so on and so forth. But this is something we had to prove from scratch in a sense, or not completely from scratch, because the pull-through formula was known for for the massive Nelson model, so we had to adapt it to this. So let me go back now. And thank you. So I think I can stop.
Thank you. Are there any questions?
Yes.
So I'm a bit confused about the scaling. So if I understood correctly, that in the dynamics you put an additional 1 over epsilon in front of the field energy.
Okay, that depends. You have it's up to you. You have two options. You can put
It's up to you.
no. You can put either 1 or 1 over epsilon. If you put 1, you see no dynamics for the field afterwards. So the field is frozen at the initial time. If you put 1 over epsilon, you see a free dynamics for the field.
If you put a 1 over epsilon in front of the field energy, doesn't that mean that, that the energy dominates the photon number? So the number of photons is finite. So how can the state be classical if you have a finite number of photons?
Well, in fact, it's not. It's even more than finite. So it goes to 0 actually in our choice, because you have anyway a control.
The number of photons goes to 0.
Yes.
So it's the vacuum we're talking about.
But no, because everything is scaled on the scale 1 over epsilon in front of it. So yeah, you have to figure it out, but it works. I mean, in fact, it is exactly classical because we are considering a limit in which the number of excitation is of scale 1 over epsilon. Of course, on that 1 over epsilon, you can multiply by something which goes to 0 and still get something large. Okay, so that's the idea. That's because of the initial rescaling. Well, I showed it at the first slide, if you remember. So I'm defining the new canonical variables with the square root of epsilon in front. And because of that, anytime I have, when I talk about, say, order, I don't know, if I have n excitation in the new variables, I have to multiply by 1 over epsilon.
I mean, in the static case, I understand that the number of photons would be something like 1 over epsilon.
Yeah.
Right? But if you, that's why in the dynamical case, I thought it's order 1. No? So what is the number of photons in the system?
Well, which kind of photons? You mean the original ones?
I know what the photons
Yeah, it's 1 over epsilon times something small. 1 over epsilon times something going to 0. That's the scaling how it goes. I'm confused.
Maybe one could think of a coherent state, which
Yeah.
one starts with number 1 over epsilon, then kind of the coupling is weak. And due to this commutation relation, the coherent state to first order would stay the coherent state. But if you, so to say, scale the field energy, then it freely evolves, so to say.
Yes, that's the way. I don't know. I mean,
one could start with a coherent state with particle number epsilon, 1 over epsilon, but then the creation
let me go.
is subleading, or. But then, so to say, if I only look, if I scale fast the field energy, then it's kind of a free evolution of this initial coherent state.
Yes.
And then it enters as a
the 1 over epsilon in front of the energy. Well, if you put there, yeah, exactly. You have enough somehow enough photons to evolve freely the initial state. If you don't put it, you don't see any evolution. Everything is frozen. So that's the way it goes, and it's encoded here in a way. So in the fact that we are from scratch basically removing or looking in a way at the number of excitation, which is something times 1 over epsilon from scratch. Yes.
Since the ground state energy diverges logarithmically, the comparison with the expected boson number should be by 1 factor of omega of k. So the boson number should diverge linearly.
I'm confused because here the boson number, you mean the number of particles in this setting. Well, that's fixed. So that's we are not taking n to infinity. I don't know if perhaps I'm missing the question. I don't know. So the okay, let me show you what it is. Here it is. So that's the self energy, and the self energy, that's the quantity of the self energy, and that gets multiplied by the number of particles, which is fixed, and this parameter epsilon. I mean, that's something you can simply copy from, if you like, from the Nelson paper, exactly what you get out of it. Then you may ask what is the behavior of it, and you see that you have a logarithmic behavior or divergence in sigma coming from the ultraviolet behavior here, which is 1 over k cubed.
Well, if you just look at the Nelson model without the particle, then you get this ground state energy by just completing the square in the creation and annihilation operators. And then you get the ground state energy. But the state that you obtain is a coherent state that, if you use it in order to calculate the expected number, you get that expression without the 1 over omega of k. And that would be linearly divergent.
So you don't expect us to see this. That's your point.
Yeah, in the number expectation.
But that's because of the okay. So and you say okay, I see what you mean now. So and you say the number of bosons for the field should diverge as that without omega. I see. Okay, thank you. Now I see. Yeah. I think should that be the case? Let me see. Yeah, I have to figure it out, but I guess you're right. Yes. So. Thanks anyway for the comment.
Other questions?
Yes.
I would have a question concerning this product states on the last slide.
Yes.
Because I thought if you test with product states, it would kind of logarithmically diverge also in the cutoff parameter.
For Nelson, yes. Yes, for Nelson, you're definitely right.
Okay, then I misunderstood. I thought.
No, for Nelson, I mean, it's obvious in a way. For Nelson is one special case of what we have already done, basically. So there's nothing to figure out. The main goal here is to do the same for Pauli fields. For Pauli fields, you do expect to see something more interesting in a way, because you don't even know what to expect actually in that case, right?
So to take product states and to see the UV divergence.
Yes. So of course it's not a full space. You are just working on a special say class of states, but still there is hope to understand something or prove at least bounds for the self-energy.
Another question?
I'm sorry, I was wrong. In the number expected number case, you get 1 over omega squared, not absence.
Okay.
So therefore, the number is flat. Okay.
1 over omega squared. That's integrable then.
Yeah, that's a thing. So it's flat.
Okay. Very good. Now it sounds better. Now it sounds much better. I'm more reassured.
Any other question? If not, then let's thank the speaker again.